Before describing node voltage analysis, let me just make a couple comments. We note that in every circuit analysis, the foundation to analyze any circuits is the connection constraints or Kirchhoff voltage laws and current laws, device constraints such as IV relationships of the various electrical elements. However, when we do this technique of element constraints and connection constraints, this involves a lot of equations and a lot of unknowns. So node voltage analysis is used to help reduce the number of equations. However, we should not abandon the idea of connection constraints as well as device constraints. All that node voltage analysis does for us, as well as mesh analysis, is to help reduce the number of equations. Now let's go through some notation. Here we have a circuit with some devices, and we have basically 4 nodes, and what I labeled here is node voltage at A, node voltage at B, and node voltage C. In here I label a ground reference point, and we always note that the ground reference point is always like 0 volts. And how do you choose that ground reference points? Well, it depends on you, but basically you try to see where most of the devices are connected, and if a node such as this has a lot of electrical devices connected to it, we usually label it as the reference node. And again, the reference node is usually 0 volts. So here we have node voltage A and voltage B, and let's say this is device 1, 2, 3, 4, and 5. Now we want to find the voltage across, let's say, element 2. Well, the voltage across element 2, we'll say V2, and this is our reference point, plus and minus in terms of our polarities. Then V2 has a voltage across that element. 2 is VA minus VB. Well, what about the voltage across V1? Well, V1 has a node voltage of VA minus 0, because the other side of this node is a ground point or reference point of 0 volts. And then V3, we have VB minus 0, or simply VB. And here for V1 we have simply VA. Now VB minus VC, so voltage across V4, again it takes 2 points. We'll choose this as a higher voltage and this is the lower voltage, as well as for device 5 and where we have the polarities of plus and minus associated with that. So V4, again, we see that it's VB minus VC, and then for V5, voltage V5, that's just VC minus 0, or 0 VB VC. So that's how you look at the node voltage analysis. Is you take your label your voltages at the various nodes. Now if V1, let's say, is a voltage source, then VA is simply equal to VS. Alright, so again, our reference node, we choose where all the elements are connected to it, and therefore we label that as has a reference voltage of 0 volts. And then to find the element voltages across the various devices, we just take the difference between those voltage points between the plus and the minus polarities. Now the diagram in the right shown here is just a relabeling of the circuit, just to show you that the voltage at VA is with respect to this ground point, voltage VB is with respect to this ground point, and voltage VC is with respect to this ground point. Again, it takes 2 voltages to represent a voltage across an element. And we see here device 1, 3, and 5 is connected to this ground point we call 0 volts, which is our reference point. So this is just our interpretation. This diagram right here is just our interpretation of this circuit. When using node voltage analysis, I need to make a couple statements at the outset. And that is, when you find a voltage V1, which is associated with a device 1, and when we use node voltage analysis, there's only two possibilities. Here in this first case, we have, let's say we want to find the voltage V1 across device 1. So V1 in this case would just be simply V1 equals to VA at one end of the device, and then the other end is connected to a reference point or 0 volts. And in this case, V1 is just simply equal to VA. Alright, so that's when you have a device, it's connected to some node in the circuit, and the other end of the device is a node that's connected to the reference point, which represents our 0 volts. Now here's a second case in which our device is not connected to the reference point, but is connected to two nodes in the circuit. That's called at node A and at node B. Now the voltage across this element V1 is just simply the difference between these two volts, and we start off with the plus and then subtract it with the minus voltage. So here V1 is just simply equal to VA, because it's connected to the positive polarity as we label it, minus VB. And that's how we define our voltages using the node voltages across the device. So our voltage V1 across the device is defined in terms of our node voltages. So these are just our two possible cases. Now let's do an example of node voltage analysis. Here we're given a circuit containing 5 devices. Our reference point is defined here, and we note our reference point is defined as 0 volts, our reference node. And then we're given nodes A, B, and C, and VA is given as 5 volts, VB is given as 10 volts, and VC is given as minus 3 volts. And we're asked to find the element voltages for all 5 devices. So we have V1, V2, V3, V4, and V5. And we want to find the voltages across each of these devices. So we'll start off with V1 with the plus reference. The plus reference polarity is given as VB, and the minus end of V1 is connected to 0. So the difference between VB and 0 is just simply VB. So remember, when we want to find the voltage across device 1, it's just the voltage difference between the two nodes. One of the nodes is connected to VA, and the other node is connected to a reference node or 0 volts. Now let's do the same thing with V2. Start off with the positive polarity that's connected to 0 volts, and we're going to subtract VC. But VC is equal to minus 3 volts, so it's 0 minus 3 is equal to 3 volts. V3, we have VB minus VC, so it's not connected to a reference node. So here we start off with the positive polarity, and the positive polarity is connected to node B, so that's just voltage B minus VC, but VB is given as 10 volts minus 3 again for VC, and that's equal to 13 volts. V4 is connected to VA at the positive polarity, and the negative polarity is connected to VC minus VC, so as VA is given as 5 volts minus 3, which is equal to 8 volts. And then finally V5, the plus side is connected to VA, and the negative side is connected to VB, and we're given VA as 5 volts and VB as 10 volts, or minus 10 volts is the difference between these two, which is equal to minus 5 volts. So that's how you do node voltage analysis associated with this circuit, and that concludes this example.